Welcome to another course of continuing education for professional engineers. In this course, we will talk about natural gas liquefaction systems, cascade, single mixed refrigerant, dual mixed refrigerant, C3MR, closed nitrogen expansion systems, and open expansion systems. This is course 8 of 10 on LNG intermediate learning, continuing education for professional engineers. A little bit of information about myself. I'm a PhD in mechanical engineering. I have a master's degree in both mechanical engineering and civil engineering. I've taught undergraduate and graduate level engineering courses at a university level. I have 52 years of gas industry experience. I retired from Keyspan Energy in 2004 as Vice President and Chief Engineer. Today they're known as National Grid. I have 20 years of international and domestic experience in teaching and consulting on LNG projects across the country and around the world. I have a passion for LNG safety, for developing human resources, and for ensuring that our gas industry is reliable. If you can understand how your car air conditioner system works, you will understand how your 150,000 horsepower liquefaction system works. Or if you're a small peak shaver, how your 5 million standard cubic foot per day liquefaction system works. Let's take a look at your car air conditioner. We'll start off with the compressor. You know what that is? You open your hood and you see the rotating compressor that clutches in and clutches out. Well, it clutches in every time it needs to provide additional air conditioning, and it clutches out when the refrigerant pressure in your evaporator gets too low in pressure or too cold, so that it clicks in and out, maintaining your car's temperature. So your compressor is shown here, and that is the compressor that's driven by a belt underneath your hood. And what comes out of the compressor is hot refrigerant. In the case of your car air conditioner, using R134A, and that is sent to a radiator that is right in front. It's the frontmost radiator under your hood, and that is called a condenser. Now, what's actually happening here in this radiator is that this hot vapor, maybe it's about 200 degrees Fahrenheit, this hot vapor goes into this condenser, and it cools down, and then it condenses into a liquid. Then 100% liquid refrigerant, I say 100% liquid, meaning it's all liquid, goes into a JT valve, which is nothing more than a restriction in the pipe. And that JT valve drops the pressure. When it does that, this refrigerant, which is maybe it's at, let's say, 100 degrees Fahrenheit and 200 psi, just to pick a number, goes into this JT valve and flashes down to a lower pressure. Perhaps it's 35 psi and 35 degrees Fahrenheit. Now, it went from 100 degrees Fahrenheit to 35 degrees Fahrenheit because it dropped in pressure and flashed. This 100% liquid is now liquid and vapor. And that liquid and vapor then are sent to the evaporator. That's underneath your dashboard. And that is cooling the air that's in your car. So the liquid and vapor come in here at about 35 degrees Fahrenheit and come out of here maybe at 50 degrees Fahrenheit. Meanwhile, your air from the car comes into the evaporator at, let's say, 80 degrees Fahrenheit and leaves at 55 degrees Fahrenheit, cooling down your car. And then this refrigerant, which is 100% vapor now, because that refrigerant boiled off, goes to your compressor, and the cycle starts all over again. So let's take a look at the same refrigerant process on a pH diagram. That's pressure enthalpy. And I'm showing pressure on the y-axis and enthalpy on the x-axis. And the enthalpy is nothing more than the thermodynamic energy of the working fluid, which in our case happens to be R134A. We enter the compressor at approximately 50 degrees Fahrenheit, and that's the R134A that's coming out of the evaporator coil, and it's being compressed up and it's to some higher pressure. In this case, I've selected 200 psi, and I'm looking at a temperature of 160 degrees Fahrenheit. It could be much higher than that or much less than that, depending upon the outside ambient conditions, but in this case, I've selected 160 degrees Fahrenheit. Now, I'll mention that it cannot be less than the isentropic compression, and we will talk about that later. But for now, let's just look at it as the process that we're studying. Come out here at 160 degrees Fahrenheit. What is it here? It is a 100% gas. What was it here? 100% gas. If you remember the pH diagram, this is all liquid, this is all gas, and this is a combination of liquid and gas. So now we start cooling it down, and this could be called an aftercooler, but for simplicity, in your automobile, it's discussed as it's called the condenser. But this is doing aftercooling first, which is cooling down the gas, and then the gas starts turning into a liquid. And it goes more and more of the gas turns into a liquid until you get to this point here, and you're 100% liquid, and then you cool it even further, becomes a subcooled liquid. Then you flash across a JT valve, which is a constant enthalpy process, and you go into the evaporator coil. The evaporator coil is under your car dashboard. And in the evaporator coil, you cool down the car that's in the air and you actually heat up. You actually change phase of this refrigerant from liquid and gas, which it is here, to 100% gas, which it is here. Now, in reality, when you come down the JT valve, you don't have a substance that has this enthalpy. What you really have is two substances. You have liquid refrigerant with these properties, and you have a vapor refrigerant with these properties. But it's shown here as being at this point. And that refrigerant warms up and goes back into the compressor, and the process starts all over again. That's your car air conditioner in a simplified. In the earlier slide, I mentioned that the enthalpy is constant when going across the JT valve. And here's why. According to the first law of thermodynamics, if you go through a process and you do not exchange heat or put in any work or take out any work, according to the first law of thermodynamics, the energy in has to equal the energy out. And that is the enthalpy in has to equal the enthalpy out. So let's take a look at this process here. I'm looking at the conditions that I had shown earlier, which were 100 degrees Fahrenheit and 35 degrees Fahrenheit, 200 psi, 45 psi, and those are absolute. And look at the enthalpy. Well, the enthalpy was 108.86, and it remains 108.86. So from that, I can look at the temperature that comes out. In other words, of starting here, I put in these inputs of 100 degrees Fahrenheit and 200 psi absolute, and I read out the enthalpy, type in the enthalpy, the same exact enthalpy down here, and it produces this line 2. You can see from that that the temperature is 35, approximately 35 degrees Fahrenheit, and you could look at all of the other parameters as needed, depending upon how deep you're going to analyze the process. Let's follow that constant enthalpy process a little closer. We have an enthalpy here, which is exactly the same as the enthalpy here. In the case that we're studying, we looked at 108.86 BTUs per pound. Now, what I said earlier is that it's really not this fluid right here. It's really saturated liquid and saturated vapor. And saturated vapor has its enthalpy associated with it, and saturated liquid has its enthalpy associated with it. So if I drop 1 pound of R134A across this JT valve, I would end up with less than a pound of R134A liquid and less than a pound of R134A vapor. But the sum of the vapor and the liquid would be that 1 pound. And if I took the mass of liquid times this enthalpy and the mass of vapor times this enthalpy, I'd end up getting 1 pound times this enthalpy. So let us do an analysis of this car air conditioning system that uses 134A, refrigerant 134A. And you can use any thermodynamics program. I chose to use REFPROP, REFPROP, and that's made by NIST, National Institute of Science and Technology. It's a relatively inexpensive program that is very user-friendly. Let's take a starting point. You can pick a starting point anywhere within the air conditioning system. I chose to start at the inlet to the compressor. What are the conditions at the inlet to the compressor? With 50 degrees Fahrenheit and 45 psi absolute, which if you put your gauges up, it would read 30 psi or approximately because your atmospheric pressure is 14.73 in that order of magnitude. And as soon as you put in two intensive properties, if you remember, are properties that don't change as you cut the volume in half. Pressure doesn't change, temperature doesn't change, density doesn't change, specific volume doesn't change, specific entropy, specific enthalpy, all those specifics, which mean unit per pound, don't change, and then pressure and temperature, of course, don't change as you cut the volume. So once you put in two intensive properties, you will find, once you put these two in, these other three populate. Now, I could have had another 7 rows of properties out here, but I chose to display only density, enthalpy, and entropy. So we're starting out at this point here. This is our starting point, and our starting enthalpy would be 175.13. Now, what is that? That's the energy at that point. Now, is it actually the energy at that point? Well, it depends. It is compared to some reference state that the operator puts into the program. So it says it, if I call this point 0, then this point here would be 175.13. However, if I made 0 1 unit less, then this would be 175.13. This all depends on the reference point, because in thermodynamics, what you're looking at is the change in enthalpy, not the absolute value of it. So you may have two different computers operating with two different programs and coming out with different enthalpy, but their change in enthalpy will always be the same as you go across the process, and that's what's important. So on the table that we just looked at, we analyzed this point right here, which is the inlet to the compressor. You remember we started out, we had the inlet to the compressor over here, and then we compressed up. It's not shown on this diagram. And we went across and cooled, and then went across a JT valve. We're at 35 degrees. So looking at that, I can now take this point here. How do I know the intensive properties at this point here? Well, I know one of them is 35 degrees Fahrenheit, and I know the other one is, well, we know it was 45 psi absolute, but I can also say another thing. I say it's 35 degrees Fahrenheit, and this point is also the saturated vapor. That's another property of that fluid, saturated vapor at this point. Or I could say 35 degrees Fahrenheit, and this point we know is saturated liquid. So looking at this diagram, I can say this here is my JT valve. I come down here, and that's got to be a vertical line because we already stated that the enthalpy drop across the JT valve is 0. So the enthalpy here has been calculated, and it's exactly the same as the enthalpy here. How did we calculate the enthalpy here? We knew the pressure and the temperature, two intensive properties. How did we calculate the enthalpy here? We said it's exactly the same as here. Now, what's here is the fluid actually here? No. It comes in here as 100% liquid, flashes to liquid and vapor, and here's our liquid properties, and here's our vapor properties. The point of this slide is to show that as you put this fluid through your chiller, all of, or the majority of, the cooling comes from that liquid, which is changing phase. So you get the latent heat of vaporization, changing phase, extracting heat from the evaporator. The evaporator is sometimes called a chiller. The vapor that comes out of this flash has this property, and the amount of chilling that's available is just this little bit from here to here. So this is showing the cooling that's available from the vapor as that little bit, and the cooling that's available from the liquid as this much larger value. This is a more detailed drawing of the same thing we were just talking about, except this one is done by computer-generated drawing versus a hand-generated drawing. And if you look at here, what we just calculated was this point here, which was the inlet to the compressor. What other points can we talk about? Well, I did in the other drawing talk about the inlet to the JT valve. And here it is. It's subcooled LNG at 200 psi absolute and 100 degrees Fahrenheit. Again, two intensive properties. And so this could be another point where you could have started the analysis, but we had chosen to start it here. So now looking at this, you got the same thing, a temperature drop, which is caused by the pressure drop. And this is 100% liquid, but this is liquid and vapor. Where are the liquid properties? Liquid properties are over here. Where are the vapor properties? The vapor properties are over here. And you can look at on the chart as well as by way of table. You can do in tabular form, which is more accurate. And you can read that the enthalpy of the saturated liquid at 45 psia is as shown here. This is the saturated liquid at 45 psi. This is the enthalpy before the JT valve and after the JT valve. This is the saturated vapor enthalpy, which is right here. Actually, we're reading right here, but this is the saturated vapor of the R134A at 35 degrees Fahrenheit, and this shows the saturated vapor enthalpy, which is right down here. And the way you read those enthalpies, remember the enthalpy is a vertical line. So you read it by dropping down a straight line, dropping down a straight line, dropping down a straight line. And I've put in here all of the different terminologies that's associated with it, and with each of those, you can read an enthalpy, either read it off the chart, but it's much more accurate to read it tabular. So use the computation features of the software. Now we're looking at the hand-drawn sketch of the pressure enthalpy diagram, and you'll see some additional information that I've put in here. I've shown this curved line, and that is your compressor line. Now, I haven't mentioned to you yet lines of constant entropy, and we'll be talking about that momentarily. But your compression line is never constant entropy in the real world, but in the ideal world, if we had such a thing as an adiabatic isentropic compressor, this would be a line of constant entropy. A line of constant entropy would look something like this. It would always fall on this side of the real compressor. We'll talk more about that in detail. But what's the work that's put into the compressor? It is the change in enthalpy. So every time I talk about enthalpy, I'll be talking about the change. Remember before we said here this was 173.15, I believe the number was. And at that point, it was in that order of magnitude. And really, we don't care what that number is. What we care about is the change of that number from this point to this point for doing the computation. Because the actual number here is based on some reference point that was arbitrarily selected. Let's say I selected here to be that reference point. Well, this would be the enthalpy that's computed based on this reference point, and this would be the enthalpy based on this reference point. And the change in enthalpy would be as shown here. Where do you read the enthalpy? Along the x-axis. So now we're looking at our hardware again. This is the compressor, which we just looked at how its work was shown on the pH diagram. This is the aftercooler, and again, we would look at the change in enthalpy of the aftercooler. For our analysis, this would be considered a constant pressure heat removal process. And in removing that heat, this vapor, hot vapor, becomes a warm liquid, 100% liquid. And remember, at this point, we're at the inlet to the JT valve, so we're just left of the saturated liquid line. So this should be 100% liquid, drops in pressure, the vertical line going down, constant enthalpy. Why is it constant enthalpy? Well, by the first law of thermodynamics, it's a device that has flow going through it, that has no work being added or removed, and no heat being added or removed. So it's a constant enthalpy. Whatever the enthalpy is here, it is also here. From there, it goes to the evaporator. That's your heat exchanger that's underneath the dashboard of your car. And here we have heat being removed from the car cabin and going into the evaporator. And so what's happening to the enthalpy? Well, the adding energy, it's increasing. Now you have a higher enthalpy here than you have here. That fluid then goes to the compressor, and the process starts all over again. Remember, I said earlier that you don't get much refrigeration out of the vapor. But in a car air conditioner, they want to keep things relatively inexpensive. So they do send the vapor and the liquid through the chiller, through the evaporator. Now, I say that bluntly. I really should say in most cars, they send it through the evaporator. Sometimes it's separated. But why would we separate the vapor from the liquid before sending it to the evaporator? Here's the evaporator. Here's your compressor, your condenser, JT valve, and here's a separator. Well, if you're not going to get much refrigeration out of the vapor, you might as well send it right back to the compressor. You might say, why not? There is uh, a little bit of chilling available in that vapor. Yes, there is. But if you send it along into your evaporator has to be able to handle additional flow because the vapor takes up a large space, even though it's a small amount of mass, it takes up a large space. So your evaporator needs to be larger, and sending this vapor gives you very little benefit. So it becomes more of an economic question. Do you really want to make a larger evaporator to handle that extra vapor that's going to be coming through? Now, eventually, this evaporator will be handling vapor because even with 100% liquid coming in, you're going to end up extracting heat from your cabin of your car, and that heat is going to boil off this liquid until it's 100% vapor here. But the real cooling effect comes from the liquid. So in this case, it's showing to make this a little more cost effective, the vapor has been separated and is being sent back into the compressor. Let's say that in our car air conditioning system, we also want to keep a freezer box so that when we go to grandma's and we bring her some frozen meatballs, they stay frozen and we can then put them into her freezer. So we can go to a lower pressure. In this case, let's say originally we want the car air conditioner to be operating at 35 degrees Fahrenheit. So we operate this system at 45 psi absolute, and we get 35-degree R134A coming through here. 134A comes through here at 35 degrees Fahrenheit. And we also take a slipstream of that and go to even lower pressure. In this case, we're going down to 20 psi absolute. And that 20 psi equates to 0 degrees Fahrenheit. And we fill our refrigerator, our ice box, I should say. So we have our ice box here, our freezer, and we go back to our compressor. We have our air conditioning here. We go back to our compressor. Now this is a method of getting to lower temperatures. What we did was we lowered the pressure. And then you can only go so far in lowering the pressure. The lower the pressure is at the inlet to the compressor, now you notice that I went to two different sections of the compressor. The lower the pressure is, the larger the compressor needs to be. And the reason is because the volume becomes much greater for a pound of refrigerant, and the compressor can get huge and uneconomical. So there'll come a point in time when we need to change the refrigerant that we're using. We'll talk about that. Now, this process that I've shown here for making air conditioning and freezing with the same piece of equipment is also used if you have a constant stream of fluid that you want to cool down efficiently. If I had a fluid that I wanted to cool down to, let's say, 0 degrees Fahrenheit, and the fluid comes in at, let's say, 60 degrees Fahrenheit, well, it is ideal to come in at 60 degrees Fahrenheit, first cool it down to 35 degrees Fahrenheit, or using this 35-degree Fahrenheit stream, and maybe you'll get the fluid down to 40 degrees, and then use this 0 degree Fahrenheit stream, and maybe you'll get the fluid down to 10 degrees, and that is a dual stage process. And if you want to make it more efficient, you could put another stage in here and bring that fluid down to 50 degrees, then bring it down to 40 degrees, then bring it down to 10 degrees. You could have put an infinite number of stages in here, but the whole thing that's going to drive this is the economics. You are much more efficient having two stages, but as you start adding more stages, you become more efficient at a higher cost and a higher cost, and you get diminishing returns. So it's an engineering question as to how many stages you want. Let's take that as this drawing shows nothing more than doing the same thing we did on the earlier slide, but now using three stages. We have three stages of compression here. We have a stage of compression, and we don't. Well, so far we've only talked about using refrigerant R134A, which is a great refrigerant for our car air conditioning system. But if you want to go to lower temperatures, you saw before we went to 0 degrees Fahrenheit, but our refrigerant pressure was only 20 psi absolute. That's 5 psi gauge. At 5 psi gauge, the refrigerant is not very dense. So your compressor needs to be rather large to take in that amount of refrigerant, so many pounds per minute or so many pounds per hour, that amount of refrigerant, such low pressure. So there's a negative of having a refrigerant that's at too low a pressure. Another negative, if your refrigerant goes below atmospheric pressure, then you run the risk of, if you have a leak, air getting into your system and destroying your entire refrigeration system. Now, the other problem you could have is most refrigerants or many refrigerants are flammable. So if you do have a leak at below atmospheric pressure, air mixes with a flammable refrigerant, and that can certainly be catastrophic in nature. So you don't want to have that happen. So you in general, you want to keep your refrigeration process, all of your refrigerant above atmospheric pressure. Now, there is one exception to that, and that is when you use water as a refrigerant. And when is water used as a refrigerant? In an absorption refrigeration system. And we're not covering that in this course, but in absorbent refrigeration, water is the refrigerant, and it runs at a vacuum, a very high vacuum. And in doing that, gets the water to low temperatures in the 30 to 40 degree Fahrenheit range. But to do that, you have to get to very low temperatures. So let's use propane as a refrigerant and go to a lower temperature. We're going to bring this propane down to minus 35 degrees Fahrenheit. And we could have done that by using a single stage. Could go press up, go through the aftercooler and extract heat from the propane, then go all the way down to this pressure here, which is about 18 psi absolute, and come across, removing heat from the fluid that we want to cool down, and then coming back up here. But it's a very inefficient process because you remember you're taking out all this refrigeration and you're doing it in a single stage. So if we want to do it in multiple stages, in this case, I happen to pick a four-stage compressor. And here the refrigerant is at 57 degrees. So let's say my fluid is coming in that I want to cool down, coming in at 80 degrees. So it'll go from 80 degrees to, let's say, 62 degrees. There'll always be a difference in temperature because you need that difference in temperature to have heat exchange exist. So when your heat exchanger, your fluid leaving this heat exchanger may be leaving at 62 degrees. It came in at 80 or 90 degrees, but it's leaving at 62 degrees. Now this 62-degree fluid goes into this next heat exchanger, and it goes from 62 degrees to 31 degrees. Goes into the next heat exchanger, goes from 31 degrees to 1 degree Fahrenheit. Goes into this next heat exchanger, goes from 1 degree Fahrenheit to 30 degrees Fahrenheit to minus 30 degrees Fahrenheit, and that's your final outlet fluid. What's happening in this chilling side of this refrigeration process? You have a four-stage compressor up here that is taking refrigerant from this stage at its associated pressure, at this stage with its lower associated pressure, this stage with its lower associated pressure, and finally at the very bottom stage, and I said the bottom stage was approximately 18 psi absolute, and that's all going into this four-stage compressor at different points in the compressor, and it's sending it the fluid through the aftercooler condenser and then through the JT valves to the various pressure levels. Let us keep in mind that eventually we want to liquefy natural gas. So let's take a look at the natural gas side of the refrigeration process. And right here I'm using methane. Natural gas is 85 to 95% methane. Sometimes you get natural gas even with 97% methane. But right now I'm using pure methane just for a simplistic view of it. So this is pure methane, it's a pure substance. I'm starting here at 60 degrees Fahrenheit, cooling it, cooling it, cooling it, cooling it. As I cool it, it's getting more dense. Its enthalpy is dropping, and it gets to a point where a liquid starts to form. And now I'm 99.9% vapor and a touch of liquid, just a misting of liquid. Now I have more and more liquid in this flow, more and more liquid. Here I'm about I'd say 50% liquid and 50% vapor. Up here it would be, and I'm moving along at more and more liquid. Now I am what's called a saturated liquid. That means it's all liquid, but it's at its boiling point. Here was a saturated vapor. It was all vapor at its condensing point. So keep in mind, this is all vapor shown here. This is all liquid shown here. And somewhere within this dome is mixtures, different mixtures of vapor and liquid, and they're shown at different pressures. In this case, this is a logarithmic scale on the vertical axis. So this is 100 psi, 200 psi, 300 psi, 400 psi is what I'm working at. And I'm bringing this liquid to be a saturated vapor, condensing it down to be a saturated liquid, cooling it down further to become a subcooled liquid, then go across a JT valve, and in doing that, I drop in temperature from minus 180 down to minus 256, which is here. Here's minus 250, here's minus 230, minus 260 would be somewhere not even showing here. This is minus 256, and minus 260 would be somewhere, I would think it right about here. But it's not showing here because I'm showing in 20-degree increments. So I'm minus 256 here. But is my LNG really here? No. LNG is liquid natural gas. That's here. So this is liquid methane, and it has an enthalpy associated. And this is vapor, saturated vapor methane. Now, what do I do with this saturated vapor? Well, I really cannot store it, so I'll extract the heat I'll extract the refrigeration that's available by transferring heat to it. I can transfer heat from this stream to this fluid. Let's say this goes out and heats up to here. Well, I can be removing heat from here to here in that process, and this vapor becomes what's called flash gas. Now, flash gas can be problematic when you have too much flash gas. How do you have too much flash gas? The warmer this is before the JT valve, let's say I was over here, the more flash gas I have. The closer that this line ends up to the saturated liquid point, the better off you are, because the more LNG you're producing and the less flash gas you're producing. So if I cool this down all the way to here and then flashed, I'd essentially produce no LNG, very, very little with these properties, but I'd produce a tremendous amount of flash, and that flash would make the LNG unusable if the LNG was a mixture to start off with. If it was 100% methane, yes, it would be usable, but if it started off as a mixture, the methane would flash out and the heavier hydrocarbons would remain. So this is just showing you what we need to do with methane. And we'll be doing this process later on. We'll see the benefits of operating at higher pressures and the benefits of operating at lower temperatures. We'll see that as we go along. If you recall, on the earlier slide, we showed a temperature of 180 degrees below zero, minus 180 degree F. And that's shown here. How do we get down to 180, minus 180 degrees Fahrenheit? Well, we can't do it with a single refrigerant. We have to use multiple refrigerants. Use a propane loop. This will get us down to, let's say, 0 degrees Fahrenheit. And we have an ethylene loop. Well, this will get us down to, let's say, minus 70 degrees Fahrenheit. And you have a methane loop, and that would get us down to in the order of minus 180 degrees Fahrenheit. Now, when I say a methane loop, what am I talking about? Well, the methane is actually the refrigerant. I'm running methane as a refrigerant in here, and I'm using ethylene as a refrigerant in this process, and propane as a refrigerant in this process. One of the negatives about these refrigerants is they're all hydrocarbons. So if you have a leak, you can have a hazardous condition. So, but unfortunately, in fact, most of the refrigerants are hydrocarbons. Even the mixed refrigerants that you see us using later on will be a mixture of hydrocarbons. So I have a propane loop, an ethylene loop, and a methane loop. This is called a cascade configuration of a refrigeration process. Why could I not use propane alone? Because I can't get the propane to a low enough temperature without going below atmospheric pressure. And even if it went below atmospheric pressure, I have to go way, way, way below to get down to anything that's anywhere near these temperatures. So to do that, you'd have to have huge equipment. It'd be totally inefficient and ineffective. So we use a propane loop, ethylene loop, and a methane loop. Now, is there anything mandatory that these other refrigerants would have to be used? Not at all. This could have been a nitrogen loop that's shown down here. This could have been some other fluid, but it has to match the requirements of the upper pressure, the lower pressure. These particular ones that are shown here are effective, and you don't want to have a refrigerant that has to go up to 2000 psi. And you don't want to have the refrigerant that has to go below zero pressure, below zero psi absolute. So these three refrigerants work fairly well for a cascade system. What I showed you earlier was just a three-level cascade system to get down to minus 180 degrees Fahrenheit. If we were trying to make LNG with that, we'd need to extract LNG at each of the processes using the propane loop and use the propane loop to cool the ethylene loop. At the ethylene loop, we cool the natural gas and we cool the methane that has to go down to the lowest temperature, minus 180. And at the lowest temperature, minus 180, we would cool only the LNG that's already been chilled by the propane and the ethylene process. This is a LNG liquid load curve. What it means is this is the amount of heat that has to be removed from the LNG. And why it's shown curved here is because LNG, or natural gas, I should say, at this point it's natural gas and at this point it's LNG. But natural gas has multiple components, some of which start to condense out at about minus 60, minus 80 degrees Fahrenheit. Like, for instance, propane. If there's any propane or heavier hydrocarbons, they'll start to drop out here at perhaps around minus 60 degrees Fahrenheit. And ethane will be dropping out all along here. And as you get to here, then you get to your methane's dropping out along here. And then you get to a point where you're 100% liquid, and then you subcool that liquid. That's the LNG liquid. Then this subcooled LNG goes through a JT valve, and you make LNG. You keep the LNG, and you send out the flash gas. Now I'm showing here the refrigeration curve in three steps. Here's your propane circuit shown here. Here's your ethane circuit shown here. And here's your methane circuit shown here. Why am I showing a fixed temperature? Because this temperature is the boiling point of propane at that specific pressure. This temperature is the boiling point of ethylene at its temperature, at its pressure. And here's the boiling point of methane at its pressure that it's operating at. All of the space in here represents inefficiency because I could have made a step here, another step here, another step here, multi-stage refrigeration systems, an infinite number of multi-stage refrigeration systems, and I'd have a super efficient process, but I couldn't afford to build it if I made an infinite number of refrigeration processes. So one way we can do this is use a propane, use ethylene, use methane, but make them at multiple steps within the process where you do a pressure drop, like we did with the propane earlier. Here we have a three-stage LNG cascade system. We have LNG coming in, or actually natural gas coming in, and becoming LNG as it's chilled in the first chiller, then chilled in the second chiller, then chilled in the third chiller, and out here we have coming LNG. Now out here we'll actually have LNG and flash gas, but I'm showing it as LNG. In these three chillers, we have three stages of chilling. We have a high pressure stage, a mid pressure stage, and a low pressure stage. In this chiller, the same thing, a high pressure stage, a mid pressure stage, and a low pressure stage. And the same in the final chiller, which would be a high pressure stage, a mid pressure stage, and a low pressure stage. This system is operating on methane as the refrigerant. This system, ethylene as the refrigerant. This system, propane as the refrigerant. Let's follow the process. Let's look at what's happening in the propane stage. We have propane being compressed, going into an aftercooler, going into this box, and in this box we have three separate JT valves. One JT valve feeds the warmest of the refrigeration processes. The next JT valve is the mid-stage refrigeration process. The next JT valve feeds the lowest pressure of the refrigeration process, which is the coldest temperature. So what we saw before was this was somewhere around 27 degrees Fahrenheit. This was somewhere around minus 2 degrees Fahrenheit. This was somewhere around minus 35 degrees Fahrenheit. What's happening in the ethylene chiller? In the ethylene chiller, we have a compressor starting out. We take this compressor, it has three separate pressure inlets. This compressor has three stages of compression, and it goes into an aftercooler, dumps heat to the atmosphere, then goes into this chiller. And in this chiller, it's chilled down against this first stage of refrigeration, second stage of refrigeration, and third stage of this refrigeration. That's happening in this box. Comes out here as cold ethylene, goes through three stages of pressure letdown: high pressure, highest pressure, mid pressure, and low pressure. And each one of these pressures is associated with a different temperature. This would be the highest of the ethylene temperatures, the mid-range temperature, the lowest of the ethylene temperatures, and the lowest of the ethylene pressures. And these are fed into the ethylene compressor, and that starts all over again. But take a look at what's happening in the ethylene compressor. It's chilling down both uh, methane and LNG, and that chilling is being done by the ethylene that's coming in this top stream, going to the JT valves. Remember when we did the propane chiller? We had coming in here the propane, which was going to be doing the chilling, and it was also chilling down the ethylene, chilling down the methane, and chilling down the natural gas. Let's take a look at the final stage. The final stage we have in here, methane is coming in here, and that methane's already been chilled down. It's quite cold, but it's not cold enough. So it goes through three JT valves. One JT valve is at the highest methane pressure. The next JT valve is at the mid-range pressure. And the last JT valve is at the lowest methane pressure. And they feed into a methane compressor, goes to an aftercooler, goes into the propane chiller, gets chilled, goes into the ethylene chiller, gets chilled, goes into the JT valve, which is your methane chiller, goes into three JT valves in here, and chills down at three different methane pressures related to three different methane temperatures. All the while that's happening, natural gas is being chilled, liquefied, subcooled, and then sent out to the JT valve where it's going to create flash and LNG. It's already LNG here, but it's at a high pressure LNG, which needs to, it's actually a subcooled LNG that needs to go through a JT valve where it will separate to just LNG and flash gas. Let us look at that on a load and refrigeration curve plot. And looking at it here, we have our first propane refrigeration, our second stage propane refrigeration, our third stage propane refrigeration. First stage ethylene refrigeration, second stage ethylene, third stage ethylene, first stage methane, second stage methane, third stage methane. What do we see different in this drawing that we saw as compared to the other drawing? Well, the space between the refrigeration line and the load line is much smaller. So this is a much more efficient process. Now we could have made this many, many steps and made it even smaller, but doing so involves a lot of hardware and it becomes impractical because all that hardware is also exchanging heat to the environment or from the environment to that hardware. So that becomes impractical. And there's an engineering balance that's made into how many stages you will need for that refrigeration. Now I selected minus 180 degrees Fahrenheit for the final temperature. That you will see later on will work in making LNG, but it's not very efficient in making LNG because when the LNG flashes, you do not get the sufficient amount of methane in the LNG product because a lot of that methane leaves as flash. And we'll see that later on in further slides. Well, it's time to put our big boy pants on and talk about this big scary word, a zeotropic mixture. There's nothing scary about zeotropic. It only means that it's a mixture of fluids that have different volatilities, different boiling points. So let's say we took a mixture of methane, ethane, and propane. Well, methane is highly volatile. It wants to flash into a vapor. Ethane is less volatile, but it's still fairly volatile. And propane is even less volatile. At atmospheric pressure, propane boils at about minus 44 degrees Fahrenheit. At atmospheric pressure, ethane boils at about minus 127 degrees atmospheric pressure, methane boils at about minus 255, 256 degrees Fahrenheit. So those are three components that can be mixed together. So if they're mixed together, they make LNG. And when you boil them off, what wants to jump out fastest? The methane does because it's the most volatile. Now, does it just jump out and then until there's no more methane left? No. So if a pound of methane drops off, or a pound of LNG boils off, it may be 99.9% methane, but you'll also have that 0.1% ethane, and you'll have a trace amount of ethane. So it boils off preferentially, not sequentially. This is a pH diagram of a zeotropic mixture. It happens to be a mixture of ethylene, nitrogen, propane, and methane. And the concentrations are 20% ethylene, 2% nitrogen, 38% propane, and 40% methane. Now, this happens to be in mass concentration. Typically, we do not use mass concentration for these calculations, but I show it here because I want to show you that when you do the computations, you can do it by mass and you can do it by percent volume or molar. Typically, we do it by molar, but this one has to be done by mass just to show that it can be done both ways. Now, when a zeotropic mixture boils off, you must realize that two things change in the mixture. Remember before we had LNG, and I said the LNG, the methane boils off at minus 255. Well, maybe the mixture that I had will be boiling off at minus 252, something warmer. Why? Because you've got the various components in it. So what changes in a zeotropic mixture as it boils off? Two things change. The composition of the mixture changes because the most volatile materials boil off preferentially first, and also the temperature of the boiling point of that mixture changes. Let's take a look what happens with this zeotropic mixture. We're starting here with the composition that was stated, as shown here. As we cool it down, we get to where the very first droplet forms. This is a saturated liquid vapor right here. It's a saturated vapor, but it's at its dew point, so the first droplet of liquid is forming. What's heavy in that first droplet of liquid? Well, a lot of propane is in it because it that's the least volatile components. So the propane is preferentially dropping out. And what's happening to the temperature? Well, the temperature is getting colder and colder because as you go along, there's less and less propane in here. And then as you go along, you'll find less and less ethylene in here. Then eventually less and less methane in here. And when you get to this point, you're almost all nitrogen in here. And finally, even the nitrogen drops out as liquid. And then you have 100% saturated liquid of this mixture. Now let's go across a JT valve. What's going to flash off preferentially? Your nitrogen and your methane are going to flash off preferentially. So you go across this JT valve and you get them down to this much lower temperature. Up here we were minus 100 degrees Fahrenheit, and here we are minus 170 degrees Fahrenheit. What I did was I just looked them halfway between here and here. This was minus 160. This is minus 180. So I'm down at minus 170 degrees Fahrenheit. What was my pressure up here? Remember, this is a logarithmic scale. So this is 100, 200, 300, 400. This started off at, looks like about 550 psi absolute. And where did it end up at? 100 psi absolute. Now, what's in here? Is this the fluid that's in here? Not really. It's really the fluid that's here and the vapor that's here. So this is a alphabet soup of what is actually in here because it's both liquid and vapor and it's at different compositions. And the liquid and the vapor are at different compositions as well. So as we heat this up, we're now doing what? As we heat this up, what's two things are changing? The composition of this fluid is changing. Why? Because the most volatile materials are boiling off first. The nitrogen and the methane are boiling off first, and the propane is kind of lingering behind. And what else is changing? The composition and the temperature. So with a mixed refrigerant or with a zeotropic mixture, as you boil off or as you condense, both the composition and the temperature of the fluid changes. So we started off here at minus 170, went to minus 160, minus 140, minus 120, minus 100, minus 80, minus 60, minus 40, and here we're about minus 30, and now we're 100% vapor. We go into a compressor, compress it up, and look at this. We now have a refrigeration system, which is identical to that car refrigeration system that I showed you in the beginning. The only difference is it's using a mixed refrigerant to get to the very low temperatures. Take a look at how great this is. We ended up going from a single component refrigerant to a cascade system to get down to these low temperatures. Now we're going back to a single refrigerant, which happens to be a mixture. We're getting down to the very low temperatures, and we don't need three stages of cascade compressors running together. We only need a single compressor, but what we've changed is the refrigerant into a mixed refrigerant. So let us look at this on a load refrigeration curve. If we do that, we see our load curve shown in black, and we see our refrigeration curve shown in red. And you look at the components that are doing the cooling. On the warm end, the component that's doing the cooling is the propane. In the mid range, we have the ethane. On the bottom end, we have the methane, and on the lowest temperature, we have the nitrogen, which means that when we come across the JT valve with our MR, The nitrogen flashes off first and produces the coldest temperatures. And when I say first, it's preferentially first because when this is flashing, yes, there are some molecules of propane that are flashing, but very few. And the methane flashes off preferentially, and there's very little nitrogen left. And the ethane flashes off preferentially. And finally, the propane flashes off preferentially. So when your last droplet of MR is boiling off, it might be 90% propane, even though it started off with some much lower concentration. Take a look at the cooling curve of the refrigerant. It's shown here in red, and I'll show you a couple of components or a couple of concepts related to it that are good and bad. One is that there's very little distance between the two. That's great because that means it's high efficiency. Here it gets a little bit mismatched, so it's larger, it's less efficiency here, less efficiency here. Now you can improve this by modifying the refrigerant components and by modifying the refrigerant composition. But you have to watch out. You see this right here and right here? You have to watch out not to have what's called a pinch point, where this curve gets on the other side of the load curve. Your refrigeration gets on the other side of the load curve, your refrigeration process essentially stops because it's trying to go in reverse. Heat only transfers in one direction from hot to cold. So you got to watch out for pinch points, and that's all part of the design. And would be your load and refrigeration curve as shown for the process that we just showed. Well, with that information available, we can now build ourselves a conceptual mixed refrigerant liquefier. Let's do that. Start off with a compressor, an MR compressor, and that compressor will take MR vapor and compress it into a hot vapor, higher pressure, higher temperature vapor. And we want to get rid of that heat, so it goes through an aftercooler for heat removal. But now that we're at a higher pressure, when we remove heat, we end up with MR being a liquid and a vapor. Then we go into this heat exchanger and we cool down the MR even further to make it 100% MR liquid. And then we go through a JT valve where it flashes to an MR liquid and vapor, but at a much colder temperature. And then we extract heat, use that cold temperature MR to extract heat from these two streams. We're extracting heat from this stream and we're extracting heat from this stream. This stream, we extracted heat to make it from a liquid and a vapor to 100% liquid. And this stream, we extracted heat to make it from a LNG or natural gas vapor to 100% liquid LNG. Now, still at high pressure, so you go through a JT valve and you separate the LNG to flash gas, getting rid of the flash gas and storing the LNG. Very simplistic process, but it's too simplistic. There's a lot more to an MR system than what's shown here. So let's take it a step. This is the same exact process, but it has a little more added information. We have our compressor, we have our aftercooler. Now we have a refrigerant separator that takes the MRL liquid and the MRV vapor and separates it. And then it recombines it. And why would you do that? You separate it and then recombine it. Well, it's done this way so that you can control the distribution of the vapor and liquid into the various passages of the heat exchanger. So you don't end up with slugs going through the heat exchanger, but you spray this liquid in. And quite often there's a pump associated with this so that it can be sprayed in along with the vapor and get an even distribution along the heat exchanger path. So as you go through this heat exchange, you're giving up heat to this stream here. And as you're giving up heat, this becomes 100% all liquid MR. Come across this JT valve, becomes a much colder temperature, MR liquid and vapor. And it extracts heat from these two streams. From this stream, it extracts heat. and from this stream it extracts heat. And that heat makes this become 100% vapor. So now the MR at 100% vapor goes into a suction drum. You do that to make sure no traces of liquid may carry over and damage the compressor. And then from there, it goes into your compressor. And then from your compressor into your aftercooler, and the process starts all over. Let's take a look at what's happening at the LNG end of this heat exchange. We have pre-treated feed gas. That means all the CO2, H2O, mercury, and water vapor have been taken out of it. That comes in here at 40 degrees Fahrenheit, is chilled somewhere around maybe minus 70 degrees Fahrenheit, goes to a heavies knockout because we still have in here some heavy hydrocarbons, hexanes and heptanes, maybe an octane in there, but you certainly want to get out things like benzene, ethylbenzene, xylene, toluene. So you want to make sure that you have a heavies separated that takes place here, and that knocks out your heavier hydrocarbons. Your heavy hydrocarbons go for processing, and then your gas stream continues on to be made into LNG. If you don't take out those heavy hydrocarbons, they will freeze up in this part of the heat exchanger. So you have now LNG being produced using an MR compressor. Something very wrong here. You're going to go from 100 psi to 750 or so psi in one stage? Not really. So let's put in multiple stages of compression and do some other finessing. Before we add multiple stages of compression, let's just take a look at a pH diagram. And this one happens to be in molar percent, not mass percent. And you can know that with this program because it's showing decimal points here rather than whole numbers. So this one happens to be 15 molar percent. Another way to say molar percent would be volume percent of nitrogen, 20 molar percent of methane, 35 molar percent of ethane, 30% of propane, and that's molar percent. So let's take a look at the process. We compress the gas way up, high temperature, high pressure. We go into aftercooling. This is cooling to the atmosphere. And at some point, we're going to be cooling to this stream below here. Once we get below ambient temperature, the only place we can cool to would be to this stream that's down here. And we're cooling right now. You're still using ambient air, and we start using this stream to do refrigeration uh, of this flow stream, and we're cooling this further and further and further and further and further till we get to here, which looks like about minus 210 degrees Fahrenheit. Drop across a JT valve, we come out here at what looks like to be minus 238. I'll estimate it as minus 238 degrees Fahrenheit. And now I start using this stream to absorb heat. Where am I absorbing heat from? From this stream. How do you think it got so cold? This stream got cold while this stream got heated. And I keep on producing that refrigeration by letting this boil off, and it's extracting heat from this stream to this stream, and it continues to boil off until we get to a point here, which is at about 85 degrees Fahrenheit, and then you compress up again, and the process continues. How much of this cooling that's available, this is all cooling that's available, how much of this cooling went to make LNG and how much went to chill the MR? This amount went to chill the MR from here to here. So this amount, 235 BTU per pound, went to chill the MR, and 285 total was available. So we have about 50 BTU per pound of the MR that's available for making LNG. And now, is it making it all with this chilling part? No. When this is extracting heat from here, it's also extracting heat from the LNG. All along this process, it's extracting heat from the LNG. or from the natural gas that's going to be made into LNG. And at the same time, at this point here, it's extracting heat from the MR that needs to be chilled. Now, this is a zeotropic gas, which happens to be pipeline gas that's been cleaned up and you want to liquefy it. It contains 94% methane, 5% ethane, 1% propane, and those are all molar percentages. And if you see, we're here 94% C1. That's methane. It's got one carbon atom, C1. That's the shorthand usage in the gas industry. 5% C2. That's 5% ethane. Remember, ethane is C2H6, and 1% C3. Remember, that's propane. Propane is C3H8. That's why it's called C3. So you have this mixture of natural gas that's been cleaned up, meaning the CO2, water vapor, mercury, hydrogen sulfide, and any other contaminants, solid contaminants have been removed. Heavy hydrocarbon removed, gets put back in, the gas gets put back in, and the process continues along. So let's take that gas and cool it, cool it, cool it, cool it down. And what happens here? The very first droplet forms. What's what's the concentration of the very first droplet of LNG that forms? Here it's going to be high in ethane. Most of the propane is already knocked out. Out here it's going to be almost all methane. And out here it is the same composition as what's here because everything has now been condensed and now it is subcooled. In this case, we went to a subcooled temperature of minus 210 degrees Fahrenheit. And then we flash at this 600 psi down to tank pressure, 16.5 psi. And what do we have here? We don't have a fluid that's here. We have actually a fluid that's at this state and a fluid that's at this state. And these are the saturation states. So this is saturated vapor and this is saturated liquid. And here I want to wave my hand and say, pay attention to this next item that I highlight. This was 94% methane. The LNG is 92.6% methane. How did that happen? Well, the lightest components flashed off quicker, rapidly, and that's where this vapor came from. So look at the vapor concentration. It's 99%, 99.99% C1, and it's only 0.01% C2, and it has a trace of propane in it. So what's happening is this LNG is becoming hotter. When I say hotter, I mean it has a higher heating value. Why? Because methane has the lowest heating value of these components. C1 has a heating value of about 100 and, I'm sorry, 1,013 BTU per standard cubic foot. Ethane has a heating value of about 1,775 BTU per standard cubic foot. And propane has a heating value of approximately 2,500 BTU per standard cubic foot. So this LNG mixture has a higher BTU content than what was originally coming into the plant. That has its disadvantages, as we'll see as we go along. Where did I get that data that I just showed you? Well, I got it from RefProp. I was nothing more than a thermodynamics program, and I plotted out the pH diagram and then overlaid it with the lines that I drew onto the pH diagram. But I needed to get the values, so I went to the computational section of RefProp, and I put in for the gas of 94% methane, 5% ethane, 1% propane. That shows here methane, ethane, propane, and this shows me that it is a molar concentration. I put in the intensive properties of 600 psi absolute and minus 210 degrees Fahrenheit, and it automatically printed out this entire row, and what it shows me is that the enthalpy is 34.107. Now I know I'm going across a JT valve. JT valve is a constant enthalpy valve. So a constant enthalpy valve means the enthalpy is the same at the inlet of the valve and at the outlet of the valve. At the inlet of the valve, we have 600 psi. At the outlet of the valve, we have 16.5 psi. So I input the value 16.5 psi and I type in the value 34.107 here. So again, I have two intensive properties, the enthalpy, a specific enthalpy actually, and the pressure. And with those two intensive properties, the computer now can tell me all of the other variables, all of the other properties, I should say. And the temperature of the new fluid is minus 254 degrees Fahrenheit. The total fluid is going to be 94.51. That's the same as it went in. However, if I look at the liquid portion, initially when it's at 600 psi, it's 94, 5%, 1% liquid, but now it's 92.6% liquid methane and 6.1% liquid ethane and 1.2% liquid propane. And what is in the vapor? The flash gas, 99.985% methane, 0.014476% ethane, and just a trace amount that would be 1, 2, be 0.00035% propane. That's what's in my flash gas. But take a look at what happened to the LNG itself. It became richer in propane and richer in ethane and less rich in methane. So now we know how to make an MR liquefier. But let's say we want to make it more efficient. The easiest way to make an MR liquefier more efficient is to add more stages of compression. And that's what we've done here. We've added we have a compressor with an intercooler, a compressor with an intercooler, and a compressor with an aftercooler. Now we could have added 10 stages of compression, but then it becomes economically not viable. So 3 stages is considered to be the general rule of thumb for liquefaction processes using MR compression. And what else could we have done? Well, we could have improved the efficiency of the heat exchangers, but that's another balanced engineering decision that has to do with looking at whether you're going to increase your capex so that you can decrease your opex. What else can we do? Well, we can take the boil off gas off the tank, and it's cold. Take that boil off gas and use that as refrigeration in this process as well. Let's take a look at the process that's here on a pH diagram. On a pH diagram, it looks almost identical to what we saw earlier, except that the compression, instead of being done in a single stage going all the way out here, is now being done in 3 stages. A stage, then intercooling, another stage, then intercooling, another stage, then aftercooling, and then you continue, and at the end of the aftercooling, you have liquid and vapor. You cool that liquid and vapor down. You then drop it in pressure across a JT valve. You then warm it up by extracting heat from this MR stream and from the LNG. And then you go back to your compression stage. Now, how could I have made this even more efficient? Well, one way I could have made it even more efficient would be to put a liquid turbine in here. So instead of this being a constant enthalpy process, it would follow a position something like this here, where it provides work out, which could be used to lessen your work that needs to drive the compressors, but it would also give you a higher, I'm sorry, a lower temperature. That lower temperature could provide more refrigeration. That is actually done on some LNG facilities, but only in the very large ones like export terminals. They'll use a liquid expander here in order to extract work from the fluid, because don't forget you're at a high pressure here. And not once you extract work by the first law of thermodynamics, you're dropping the enthalpy, which means you're dropping the temperature. So it gives you more refrigeration and a byproduct of work, which you can use to either generate electricity or lessen your compression work that's needed here. Load refrigeration curve would look something like this. Now, the shape of this curve is really dependent upon the composition of your feed gas, and the shape of this curve is really dependent upon the composition of your MR. To show all the components that I've shown earlier, I added in here a phase separator and a pump to take the liquid and to spray it into the heat exchanger, and the vapor that comes in the top mixes with the sprayed liquid, and this MR then travels down the heat exchanger. It cools, goes across the JT valve, comes up here, gives up its refrigeration or absorbs heat from the other streams, and goes back to the compressors. All of this heat exchange is done in brazed aluminum plate fin heat exchangers. And those brazed fin heat exchangers are very hard to construct, very proprietary in the art of construction. And I can give you a rough idea of how it's done. The plates are plated together, and inside the plates, you'll see they have these corrugated distribution tubes and turbulent turbulation tubes, but these also conduct heat from plate to plate. And in one set, of fins, you'll have one flow going, another set of fins, you'll have another flow going. These can be made counterflow, cross flow, multiple passes, very complex exchanges, and they are compressed together. They're constructed, compressed, very machined, very accurately closed together with, and in between each seam is some flux and some braze material. The entire compressed unit is then submerged in a molten bath. The braze material melts and adheres to the aluminum, taken out of the molten bath, and then allowed to cool. And hopefully, at the end of that process, there are no leaks associated with it, because that's then tested for pass-to-pass leaks or any other type of leakage. Like, for instance, if you had leakage on the outside, it would show in this area here. And these can be made counterflow, cross flow, parallel flow, whatever configuration is needed has to be designed, then specially manufactured, and then sent out to the customer for use, of course, after testing. This is what a finished product of a brazed aluminum heat exchanger looks like. As you can see, it's a marvel of engineering and workmanship skill. However, I give you one caution, and that is that aluminum and mercury are not friendly to each other. Mercury aggressively attacks aluminum. If we started this discussion today, and I started with a drop of mercury on an aluminum plate, by this time it would be halfway eaten through that plate. Mercury is a component that needs to be removed from your feed gas, and it also needs to be removed from your MR. So that's something, a caution that I give you, because I've seen entire plants be destroyed because mercury was in the feed gas or was in the MR stream. Before we get off the topic of MR refrigeration and MR liquefaction processes, Let's stretch our imagination and do a concept drawing of a mixed refrigerant where we not only separate MRL from MRV, but we use them as two different MR streams. Let's start off with our MR compressor. Now we know that it's going to be a multiple stage compressor, but typically you have an MR compressor, an aftercooler, and you always have the ability to do an anti-surge recycle to protect the compressor. That's what this section is, this section right here. And typically you'd have multiple stages. It might be 3 stages of MR compression. Well, the MR compression under operating circumstances goes into a knockout drum, gets fed into heat exchangers, and this would be an aftercooler dumping heat to the atmosphere. And then you could have another cooling system. In fact, you have to have another cooling system so that you can separate the MRL from the MRV. Now, this other cooling system could be more ambient heat exchangers, or it could be another MR system, or it could be propane chilling. It could be a number of different types of refrigeration systems. But you want to get this MR down to where it separates MRL and MRV. Now, instead of taking your MRL and MRV and bring them into the heat exchanger and spraying them together, let's keep them two separate streams. So let's take the MRL stream. Remember now, what is MRL? It's going to be heavier in the heavy components, the lower boiling point I'm sorry, the higher boiling point components. So it'll be more the propane and the ethane in here, and the MRV would be more of the nitrogen and the methane in here. Now we'll have the other components, but it'll be a higher percentage of the more volatile components in the MRV and the less volatile components in the MRL. So the MRL would be a good candidate to do low temperature cooling, and the MRV would be a good candidate to do very low temperature cooling. So let's see what we're doing here. Take the MRL and we subcool it even further, and then we flash it across a JT valve and put it into this stream, which goes back to the compressor suction drum. And in doing that, this might be operating at maybe minus 180, minus 200 degrees Fahrenheit, but it's kind of cold and it's doing a lot of cooling in here. What's happening to our LNG stream while that's happening? Well, the LNG is coming in, it's being cooled, heavies are knocked out. We're providing reflux for the heavies to be knocked out. The heavies knockout drum is not shown in here, but it needs real clean reflux, and that's what this would be. And it's being cooled further, being cooled very cold. Here would maybe in the order of magnitude of minus 270 degrees Fahrenheit. And then we go through a JT valve, LNG to storage. Let's take a look at that MRL. The MRL came up through here, was chilled, got the J, it went through the JT valve and met up with this stream, which we haven't really talked about this stream yet. So we will do that shortly. And this is the MR going back to the compressor. Let's take a look at the MRV. That's MR vapor. Well, that consists of the more volatile components on higher percentages. That's nitrogen and methane, more nitrogen and methane than ethane and propane. And that MRV comes into this heat exchanger. It is cooled down by the MRL that has been flashed, that has been pressure dropped across the JT valve. It is cooled down by that MRL that is being boiled off here, and it keeps on cooling, and it goes into this next heat exchanger where it cools down even further and becomes a subcooled liquid. Now we have MRV which happens to no longer be a vapor, but it now is a liquid, contains a high percentage of methane and nitrogen, goes through a JT valve and flashes at a very cold temperature. It flashes at minus 280, and it goes down. It gives up its refrigeration by absorbing heat from the LNG, and absorbing heat from the MRV, then continues down. By this point, its composition has significantly changed. Instead of it being in vapor, in liquid form, being high in methane and nitrogen, now it's lost a lot of its methane and nitrogen, and it's at about the same composition in liquid form as the MRL, which has just been flashed across that JT valve. So it mixes up with the MRL and continues down this path, boiling off all of the methane, ethane, propane. I should have said nitrogen, methane, ethane, and propane. By this time, it's 100% vapor, goes back into the suction drum of the compressor. What else do I see happening here? I see these other heat exchangers. What are these? Well, we have cold boil-off gas that comes out of the off the tank or comes out of your nitrogen rejection unit if there is one, and that can be used to further cool down your MRV if it comes off a nitrogen rejection unit. If it doesn't, it may not be cold enough to cool down MRV, so it can certainly cool down this MRL. It can cool down this MRV that's over here, and it can be sent to your uh, boil-off gas compressor. Now you come out of your boil-off gas compressor, and that does not have to be heated because it can become turbine gas. And your turbine gas has to be around 220 degrees Fahrenheit in that order of magnitude because you want to make sure that your turbine gas does not have any liquids in it, any drop of oil or condensate that may have knocked out. So that what feeds your turbine is a hot gas of about 220 degrees Fahrenheit, and it depends on which turbine you're using, what the vendor recommends the temperature and pressure to be. The pressure might be in the order of magnitude of 400 psi absolute, and that's to get inside the compressor. You have to have the higher pressure, of course. Now you have exhaust from your turbine or your exhaust. You can do heat recovery. And there are many different things you can do with that heat recovery. You can generate electricity by driving a steam generator. There are many different things you can do. And you're also going to need, at times when you're not liquefying, you're still going to need an electric motor to drive this boil-off gas compressor. Let's see what else is happening with the gas that comes off this boil-off gas compressor. Well, it goes to a pipeline compressor because your pipeline might be operating at 1,000 psi. Well, we don't have 1,000 psi here, so I have a separate pipeline compressor going out to the pipeline. And once you come off a pipeline, you're going to go through a JT valve. You want to heat that gas up before it goes through a JT valve because it will see a temperature drop as it goes across that valve, and you don't want freezing gas to be in here. Another place you can get gas is from the bottoms of your demethanizer. Remember I said here that this is reflux that's going back to your cold separator? Well, you may be using a demethanizer that uses this reflux, but the demethanizer bottoms have to be treated. You may end up putting those demethanizer bottoms into your fuel gas. So that's why you have a mixing drum shown here. And this is taking what we had before as many different concepts and rolling them all into one conceptual picture of an LNG facility, a liquefaction facility. This concept need not be limited to brazed aluminum heat exchangers. It can also be used with spiral wound heat exchangers. This is the same process I'm showing here that I showed earlier with the brazed aluminum heat exchanger. Here we're showing an MR compressor. I'm only showing a single compressor, but as we know from earlier work, it would typically be 3 stages of compression. And then we're going to chill that MR, whether it be through an ambient chiller or a propane chiller or another mixed refrigerant chiller. We're going to chill that MR, separate it into MRL and MRV. The MRL would come up, become subcooled, and be used for mid-range refrigeration. This may be in the order of magnitude minus 180 to minus 200 degrees Fahrenheit, and that's going to chill these streams that are in here, chill them. And what are one of the, let's take a look at one of the streams, is your feed gas stream, which is cooled down and knocked, that liquid is knocked out. That liquid is used for reflux for your cold separator or for your demethanizer. And then the vapor that continues along is cooled down and made into subcooled LNG at high pressure, goes through a JT valve, may also go through a liquid turbine if it's a large export terminal. This might have a liquid turbine on it. Goes into an NRU, nitrogen rejection unit, if that's needed. If your gas has a high concentration of nitrogen in it, you may want to get rid of that nitrogen. Well, the off gas of this is going to be high in nitrogen, high in methane content. So you can't just discharge it, because not only does it have high methane, high nitrogen in it, but it also has high methane, so it has calorific value. So you send that cold gas, extract the refrigeration from it, and send it to what's called flash gas compressors. Those are flash gas compressors because they are the flash gas that occurs in your nitrogen rejection unit. The LNG is pumped to the LNG storage system. And let's take a look. We looked at the MRL. We did not look at the MRV. The MRV comes up and goes into this heat exchanger and is chilled, 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 chilled. In this lower section, it's chilled by the MRL, but it's also chilled in this upper section to a very cold temperature, maybe minus 270. And it then goes through a JT valve. It's 100% liquid here, goes through a JT valve, flashes across the top, could be maybe minus 280 here, and then rains down upon the spiral wound heat exchanger. And then at this point, it's at a composition where it's nearly the same as the MRL, because the MRV has boiled off a lot of its nitrogen and methane. And so now it's at a composition that's very similar to MRL. So it mixes with the MRL and keeps raining down on these coils, cooling them. And by the time it gets to the bottom, it's all vapor. Vapor is sent to the suction drum, and the process starts all over again. This vessel is typically called the main cryogenic heat exchanger. It is a vessel that has many, many tubes wrapped in a circle around a mandrel, and we may have a picture of that in the further slide. On the earlier slide, I mentioned that we're going to be pre-cooling the MR in order to get it to separate to MRL to MRV, but it also pays to pre-cool the feed gas that's coming in. If you do it using you could use an MR system, or you could use a propane pre-cooling system, and each of them has their unique advantages. This diagram shows a propane pre-cooling system associated with your MR system. You see this one's showing 3 stages of propane cooling, one here, and one here. And this could be, let's say this is 60 degrees Fahrenheit, cool down to 60 degrees. Maybe, actually, that would be your incoming gas would be 60 degrees. So this would probably be 30 degrees. This would probably be 0 degrees. This might be minus 30 degrees Fahrenheit. And what's nice about this is with your feed gas always coming into your MR system at a fixed temperature, you don't have to deal with the swings of temperature during the day where it's cold in the morning, warm midday, cold at night, warm midday, and you're adjusting your MR composition to match your load on your chilling side. You're coming in always at this fixed temperature, minus 30 degrees. And the same is true with your MR. It's always coming into the main cryogenic heat exchanger at this minus 30 degrees. I just picked that number randomly. It could be minus 20, minus 35, whatever it be. but it's going to be something that's set up by your pre-chilling system that's shown here. You wouldn't want to be minus 35 if you're using propane, because that's about as cold as you can get with propane to keep the propane still above ambient pressure. And then you have your MR process taking place here. If it's a process that's two MR streams, MRL and MRV, it should be a good match to your LNG load curve. And this is being your load curve. This is your load curve, and this is your refrigeration curve is shown here. Well, let's look at just a single MR, but let's look at it with C3 cooling as well added to it. And let's have it with three stages of compression. So we have compression, intercooling, compression, intercooling, compression, aftercooling. And the last fin-fan exchanger is typically called an aftercooler after a series of compressions. Then we have C3, which is propane chilling or propane cooling, all the way down to a temperature of around minus 35 degrees Fahrenheit. Then you continue chilling the MR. Where does this extra refrigeration come from? It comes from your MR after the JT valve. That continues cooling down your MR till it becomes fully subcooled MR. Flash across the JT valve. This looks here like about minus 210 degrees Fahrenheit. And this here looks like to be about minus 238 degrees Fahrenheit. And then you start giving up that refrigeration or extracting heat from two locations. You extract heat from your MR stream and also from your feed gas stream that is going to be made into LNG. So you extract heat from your feed gas stream and from your MR stream. And how much heat do you need to do your MR cooling? You need 95 BTU per pound. Why? Because all the rest of the cooling was done by the aftercooler and by the C3 system, the propane cooling system. That means that for the total amount of cooling that's available, 285 BTU per pound mass, 95 BTU per pound mass is used to chill the MR, which leaves 190 BTU per pound mass to make LNG. This is a very compact and efficient kind of way of approaching making LNG using both C3 chiller or propane chiller and MR process. And it would be optimized if you were to then separate the MRL from the MRV and do it in two processes. But I only showed it here as a single process. This is a graphic I made of a MR system used to liquefy natural gas that has a four-stage propane pre-chiller. And you can see there's four stages, 1, 2, 3, 4. And of course, you'd have suction drums and you'd have chillers. And take note that the chillers separate the liquid from the vapor because you have liquid coming into the chiller. Here, you get a JT valve. You have liquid coming into the chiller, and chiller is a vessel that has liquid, a vapor on the top and liquid on the bottom. So the vapor goes up the top and the liquid goes on to the next JT valve. And then again, the vapor is separated, vapor goes up the top, liquid goes to the next JT valve, and so on, until you get to the final JT valve, and it becomes all vapor that is then fed up to your suction drum. And the MR goes through three stages of MR treatment. Oops, I did that wrong. Here I'm showing a hypothetical mixed refrigerant. And this mixed refrigerant consists of nitrogen, methane, ethane, propane, and the composition is 15 molar percent of nitrogen, 20 molar percent of methane, 35 molar percent of ethane, 30 molar percent of propane. And that's shown down here as the total molar percentage here. 15 of nitrogen, 20 of methane, 35 ethane, and 30% of propane. Now, if I chill that down to minus 30 degrees Fahrenheit and at a pressure of 781 psi absolute, and remember where we got that 781, we had 3 stages of compression, with each stage of compression being a fixed number, and it brought us up to the 781. We're going to get 2 separate fluids. We're going to get a liquid phase and we're going to get a vapor phase. And what would we expect? In the vapor phase, we'd expect to have a higher percentage of the more volatile components. What are the more volatile components? The nitrogen and the methane. And in the liquid phase, we'd expect to get a higher percentage of the less volatile components, such as the ethane and the propane. Well, let's take a look. Nitrogen went from 15%. In the liquid phase, it went down to 7%. And in the vapor phase, it's all the way up to 50%. The methane went from 20%. In the vapor phase, it went up to 34%. And you expect it to go down in the liquid phase, and it does, down to 17%. And the propane, you'd expect that to go up in the liquid phase, which it does, up to 36%, and down in the vapor phase, which it does, which goes from 30% down to 3%. Now these 2 separate MR mixtures of different compositions can be used in a heat exchanger for different levels of refrigeration. The MRL would be used for cold refrigeration, and the MRV would be used for very cold refrigeration. Now let's take a look at the MRL and the refrigeration that's going to be accomplished using the MRL. Now remember, MRL starts off as a liquid. So looking at this phase diagram, this pressure enthalpy diagram, we see that the MRL starts out over here at minus 30 degrees Fahrenheit. So at minus 30 degrees Fahrenheit, it cools down further in the heat exchanger. What is it becoming? A subcooled liquid. Becomes a subcooled liquid down to minus 160 degrees Fahrenheit. And these are all hypothetical numbers, but these are the process. This is the process that I designed in order to do this presentation. So down to minus 160 degrees Fahrenheit. We flash across a JT valve. It becomes minus 180 degrees Fahrenheit, and now it's a liquid and a vapor, and it starts absorbing heat from the natural gas and from the MR streams. It absorbs heat from the MRL, it absorbs heat from the MRV, and it absorbs heat from the natural gas, with all that heat going into this MRL liquid and vapor. When it gets to be a temperature of around minus 140 degrees for the process that I designed, be different for every process, and you see where I got this minus 140 from. I'm just reading the temperature line that's shown here. It's going to mix with the MRV. And we haven't explained the MRV yet, so you'll see why it mixes with the MRV. And what's happening to the concentration of this MRL as it boils off? As it boils off, it's becoming heavier and heavier. More of the less volatile components are remaining as liquid, but more of the high volatile components are exiting. And it's got a certain composition here, which you'll see will match the composition of the MRV in the next slide. So let's go to the next slide and look at MRV. This is a pressure enthalpy diagram of the MRV. The MRV, if you look at it, it says V, meaning vapor, starts off as a vapor. So it's on the saturated vapor line. And as this cools down and it's cooling down in the MCHE, which is the main cryogenic heat exchanger. It's becoming a liquid, more and more liquid. It's vapor and liquid. But finally, it gets to the point where it's 100% liquid. Then it becomes subcools. Now it's a subcooled liquid down to minus 240 degrees Fahrenheit. Where did we get such a cold temperature from? Let me show you that minus 240 degree MRV, which is now 100% liquid, goes across the JT valve and drops to about minus 285 degrees Fahrenheit. So it's quite cold here. So it's absorbing heat from this stream to get it down to the minus 240. And it continues to warm up as it absorbs heat both from the MRV and from the MRL stream and from the natural gas stream, which we want to use the natural gas to become LNG. It's a feed gas. I shouldn't say natural gas. I'll call it feed gas. And that feed gas is getting colder and colder because it's giving up its heat to this MRV and to the MRL, which we saw in the earlier slide. And when this MRV gets to a point here where it's about minus 140 degrees, same as we had in the earlier slide, it mixes with the MRL and becomes just MR, which has more cooling remaining in it. So the two streams mixed together now continue on cooling until it gets close to the temperature that the feed gas is coming into the process at. So let's select an MR mixture. Here's MR. The MR stands for mixed refrigerant. And these are the typical components that are used in an MR mixture. Now, not all of them are used in a mixture, and it depends on a number of variables as to which of these components you will select. Almost all MR mixtures contain some nitrogen and methane, and that's because you want to get down to the real cold temperatures, colder than minus 260. And the ideal is to get your feed gas down to minus 260 so that you have little or no flash gas occurring when you go across your JT valve with your feed gas becomes 100% subcooled liquid, goes across the JT valve and becomes a mixture of flash gas and liquid methane or liquid LNG, natural gas, liquid natural gas. But if you're real cold, get down to like minus 260, the flash gas is minimized. Actually, you can end up with no flash gas if you're cold enough, just 100% LNG being produced. So if you're having a pre-treatment, pre-cooling, I should say, of the MR, like we did earlier, we brought it down to minus 30 degrees. Your typical composition would be nitrogen, methane, ethane, and propane. If you're using an ambient condenser for your MR, then you'd also have isopentane and propylene, and ethylene in your mixture, along with methane and nitrogen. You still need the methane and nitrogen in order to get those cold temperatures, but in order to condense into a liquid and vapor at ambient temperature, you need these other components, these less volatile components of isopentane, propylene, ethylene, whatever your mix is that's matched to, you match it to both your feed gas and your condenser temperature. So far, we've spoken about refrigeration systems that use a phase change of the refrigerant. Now we're going to talk about a refrigeration system that uses just expansion and compression of a gas. In this case, it happens to be a nitrogen gas refrigeration system that was used to liquefy natural gas. How does that happen? Well, when you put gas through an expander or a turbine, and an expander and a turbine are the very same thing. They're a device that expands gas, and in doing that, it generates shaft work. Shaft work coming out of the fluid means that the enthalpy of that fluid has to drop, If the enthalpy drops, the temperature drops. So you end up getting a cold refrigeration stream by expanding a gas through an expander. And the shaft work that comes out of the expander, if you look here, is an expander. That shaft work has to be used, and in our case, we use it to drive a compressor. So let's look at this process. We'll start at this point here. This is where work comes into the main compressor. As you compress gas, it goes to a higher pressure and becomes hot. You get rid of that heat in an aftercooler. From there, it goes to a heat exchanger where it is chilled down to some colder temperature and then goes through an expander where it is expanded, produces shaft work, and comes out much colder. That real cold gas then is used to extract heat from the other gas streams that are shown here. As it comes out of this exchanger, it's been warmed up, but it's still rather cold. Goes into another expander, expands to a second level of pressure, and this is a lower pressure yet, and more work is produced, which drives another compressor. This gas comes out of here very cold and is used as a refrigerant for the other gas stream that is shown here, that is the blue gas stream. It extracts heat out of this blue gas. And it's not really blue gas, that is feed gas. And as it travels up, it extracts more heat from the feed gas and it travels up and it extracts more heat from the feed gas until it comes out rather warm, almost the temperature of the feed gas itself. And then that nitrogen is sent into a compressor where it's compressed, then goes into an intercooler. Now, this one's not called an aftercooler, it's called an intercooler because it's between two compressors. So it goes into the intercooler, rejects heat, goes into another compressor, goes into another intercooler, rejects heat, and then goes back to where we started. So take a look at the pressures. This is the highest pressure. Then it goes through here, drops down to a lower pressure, goes through here, drops down to a lower pressure yet, gives up its refrigeration by extracting heat from the feed gas. Then it gets compressed up to a higher pressure, then to a higher pressure yet, then to the highest pressure in this nitrogen loop. And this loop continues using the same nitrogen. So there's no nitrogen consumption in this process. There is some nitrogen loss at the compressor seals and at the expander seals. And that nitrogen loss goes to the atmosphere. And it's no concern about it being flammable because it's nitrogen, but there is concern that it has to be in an area that is ventilated so that you don't end up having an enclosed space with nitrogen buildup. Let's take a look at this process, what's happening with the feed gas. Feed gas comes in, it's been pre-treated. It doesn't have anything in it that will freeze up. It gets cold, then it gets colder yet, becomes a subcooled liquid as it comes out of here. Somewhere in this exchanger or at the end of this exchanger, it becomes a liquid. Then it becomes subcooled, then goes to a JT valve and flashes. If it's cold enough, it flashes just to LNG. If it's below the saturation temperature of the LNG that's in the LNG tank, then it will become flash gas and LNG. They both, flash gas and the LNG, get sent to the tank, and the boil off comes back. And the boil off's cold, so you want to extract any refrigeration capacity out of that boil off gas, and you extract it in this heat exchanger, another pass within this heat exchanger. And you see there are three different levels of heat exchange being performed in this particular design. We're going to now look at some basics of how a expansion turbine works and how to do the computations related to the expansion work and temperatures. If you want more detail about the mathematics or the thermodynamic program that's being used, how to use that program, you can go to the thermodynamics course that's given by the same publisher. Let's expand across a turbine. It removes work from the fluid. If you remove work, you lower the enthalpy. You lower the enthalpy, you're lowering the temperature of that fluid. Let's take a turbine, put a control volume around it, and let's say the gas that's coming into the turbine will happen to be select nitrogen. Let's say it's at 600 psi absolute and 100 degrees Fahrenheit. And let's expand it from this pressure and temperature down to 60 psi A. And you notice I did not put a temperature because that's something we're going to have to compute. And let's say this turbine or this expander is 80% efficient. To solve for the outlet temperature of this turbine, this expander, we go to our software, our thermodynamic software, and the first thing we look for is the adiabatic isentropic work that'll come out of the expander, and then we will use the efficiency to find the real work. And in doing that, we'll be able to find the adiabatic isentropic temperature as well as the real temperature of the fluid that's coming out. And this is all based on a BTU per pound. So the more mass you put through, the more refrigeration you're going to get. But we need to look at what the enthalpy of the output gas is to know what kind of refrigeration or what level of refrigeration we're going to get. So the first thing we put in is our starting point. We know that the gas, the nitrogen, is going into the turbine or the expander at 100 degrees Fahrenheit and 600 psi absolute. And that gives us a certain enthalpy and entropy. Now, you may use a different software program and come out with different numbers. And that's because these are based on some reference state that you, as the software operator, can select. And if you don't select it, it just defaults to whatever the program has pre-selected. But what's important isn't the actual value here. What's important is the change of value. So if you use two different reference points, you may have different values, but the delta enthalpy and the delta entropy will always be the same. So that's key to remember in case you open up a software program and do not match these values, you'll know that the reference point might be different. So in this case, we start out with the gas coming into the expander with an enthalpy of 135.4. Now, the first thing we compute is the adiabatic isentropic. What does that mean? Adiabatic means no heat transfer. We put a control volume around that expander, and we said there's no heat transfer to or from that expander, so it's adiabatic. That means no heat transfer. Then we said it's isentropic. Isentropic means that it is 100% efficient. So if it's isentropic, the entropy remains the same. So I now put in this value in the entropy for the second row. And if you look at that, the entropy here is 1.3751, identical here. This is an input that I put in. What else do we know about the outlet of the expander? We know that it's 60 psi. So we put in this 60 psi, and when we hit enter, all the rest of the column populates. And we can see that the temperature coming out of this expander is minus 173 degrees Fahrenheit, quite cold. But realize this is an 80% efficient expander. So because it's 80% efficient, there's going to be less work coming out. How much work is coming out of this expander? It's the difference between the work or the enthalpy that went in versus the enthalpy that came out. So it's this value here. Now, if you take this value and you multiply it by 80% or 0.8, you get a smaller number. You take that smaller number, subtract it from here, and you get the actual enthalpy of the gas coming out. And the actual enthalpy is a higher enthalpy. Instead of being 69.7, it's 82.8. Now you put in this as one of your inputs, and this is one of your inputs, which is the pressure. So these are both known now. And when you hit enter, the rest of the row populates. And as you can see, the real temperature coming out is minus 121.5 degrees Fahrenheit. So this is how this expander works. Let's take a look at. Actually, before looking at the next component, let's look at this expander that we just analyzed on a pH diagram. Now here's a pH diagram for nitrogen. I drew a line of constant 600 psi absolute, and I drew another line of 60 psi absolute, and I drew a line of constant entropy that crosses through the 100 degree Fahrenheit 600 psi point, psi absolute point. And if you look at the ideal expander, it would follow a line of constant entropy from here to here. And if we look at a JT valve, that's constant enthalpy. That would be a vertical line. So the actual work that's extracted from a isentropic expander would be this difference between the difference in enthalpy from this point here to this point here, which is 65.667 BTUs per pound mass. That's the isentropic or ideal work. But the actual work is only 80% of that. So we see that the actual shaft work is 52.534 BTUs per pound mass. And this is nothing more than 80% of this is shown here. So this is the constant entropy expander, and this is the real world expander. And you can see the relationship. Let's do the same exact thing for a compressor. In a compressor, we have a fluid going in at 30 degrees Fahrenheit and 60 psi absolute, and being compressed up to 600 psi absolute. Now realize that these values are just selected to show the concept. Let's take a look at what that would look like on a pH diagram and on a computational analysis. So now we're going to analyze the amount of work it takes to drive this compressor. And there's two works that we're going to look at, the ideal work and the real work. Now, the ideal work would be less in magnitude than the actual work required. In other words, an ideal compressor might require 100 horsepower, but a real world compressor might require 120 horsepower. There's always losses involved. In this particular case, we happen to be dealing with an 80% efficient compressor. So let's take a look at the compressor. We'll put in the input data for the inlet is 30 degrees Fahrenheit. That's an intensive property. We need a second intensive property. We put 60 psi absolute, and the remainder of the table populates. To do the isentropic work, we have to put this entropy in as an intensive property into this cell. And what other intensive property do we know? The 600 psi outlet pressure. So we put that in, and the rest of the table populates. So the isentropic work would be the difference between 120.9 and 234.82. And that comes out to 113.8 BTU per pound. That's the isentropic work. But we know that the real work will be something different. So if we take this 113.8 divided by 0.8, we come out with 142.29. We subtract that actually we add that 142.29 to this enthalpy, and we find out our new enthalpy of the outlet of the compressor is 263.3. Let's take a look at what's happened to the temperature. In the ideal case, we have the temperature going from 30 degrees Fahrenheit to 485 degrees Fahrenheit. But in the real world case, we have the temperature going from 30 degrees Fahrenheit, almost 600, 595 degrees Fahrenheit. And why is it hotter? Because the additional work that was due to the inefficiency of that compressor went into heat energy. So that's why you see the difference in temperature here. Let's move on. Now let's take a look at that same numerical analysis, but on a pH diagram. So if we look at it on pH diagram, I've drawn here a line at 60 psi absolute, and I've drawn here a line at 600 psi absolute, and we're going to compress the gas from 60 up to 600. The starting point is 30 degrees Fahrenheit, which is shown here. We start at 30 degrees Fahrenheit, and we do an ideal adiabatic isentropic compression as shown here. And we go all the way up to here. But we know in the real world that it's not 100% efficient. It's only 80% efficient. So we divide the work, which is the ideal work, by 0.8, and we come out with the actual work required to do that compression. And we see that the new line of compression shows like this and comes up right up about here to, and it's about 595 degrees Fahrenheit, and that's shown here. And don't get mixed up by this 550. These are the lines of constant temperature. So that's related to these lines here. This is the 580. This is 610. And this is, as best as can be extrapolated, 595 degrees Fahrenheit. And you see our actual work is more than the isentropic work. Take note that for a compressor, the work required is higher than the ideal work. And for an expander, the work that comes out of the expander is less than the ideal work. It's always a loss of available energy. In this case, you have to put more energy in order to compress the gas. And in the expander's case, you get less energy out than what would be the ideal expander. Now that we understand the concept of expansion and compression, let's take a look at using that for a refrigeration system. Let's say I have a compressor here, and I compress, let's choose nitrogen, compress it to high pressure, high temperature, go through an aftercooler, get rid of that heat to the atmosphere, take that high pressure nitrogen, run it through an expander. What comes out of the expander? Work comes out of the expander and a cold nitrogen flow. Let's use that cold nitrogen flow to extract heat from some other fluid. We'll call this a chiller. Now this nitrogen that came in here cold has come out here warmer. That goes back into the compressor and the cycle starts all over again. So this is a refrigeration system. We haven't talked about how what the temperatures are, nor the pressures, but this refrigeration system, you could see in concept, will work. Now let's put some numerical values onto this refrigeration process. We'll start off by putting an inlet temperature and pressure to our compressor. Let's say this compressor compresses from 30 degrees Fahrenheit and 60 psi up to 600 psi. And let's say the ambient temperature of the day is 90 degrees. Well, what you can expect from this aftercooler is that you can't bring this gas stream down to 90 degrees, but maybe you can bring it down to 100 degrees Fahrenheit. So put 100 degrees Fahrenheit in here. which is going to be the inlet temperature of your turbine or your expander, as we will call it. And you know this temperature is going to be colder, then this temperature is going to be warmer. It's going to be 30 degrees, and the process continues around and around. Let's assume an 80% efficient compressor and an 80% efficient expander, and let's neglect pressure drop. Let us analyze the work going into the compressor. As with any component, we draw a control volume around the piece of equipment we want to analyze. In this case, it's the compressor. We know the inlet temperature, we know the inlet pressure. We know the outlet pressure, but we don't know the outlet temperature. So to evaluate this, we want to first look at the isentropic compressor and then apply the efficiency. Now let us do the compressor thermodynamic analysis. To do that, we need two intensive properties at the inlet of the compressor. What two intensive properties do we know? We know that the temperature is 30 degrees Fahrenheit and the pressure is 60 psi absolute. Once we put those two intensive properties in, the rest of the row populates. The entropy at the inlet of the compressor is 1.5104. And keep in mind, since it's an isentropic adiabatic compressor, the entropy on the outlet is going to be identical. So we put in this entropy here, type it in as 1.5104. And what other intensive property do we know about the outlet of the compressor? We know the outlet of the compressor is 600 psi absolute. Once we type in those two intensive properties, the rest of the row populates. And you see here the enthalpy at the outlet of the compressor. Keep in mind this is an adiabatic isentropic compressor, so it's an ideal compressor. The enthalpy is shown here, and the change in enthalpy is the amount of work that would come out of that, or that would be required by that compressor. Not come out of it, but would be required by that compressor. But we know that it's only 80% efficient. So it's going to take more work to actually do that compressor. So we divide this enthalpy difference by 0.8 because the compressor is only 80% efficient. And we find a new amount of work, which would be larger. And we add that amount of work to this enthalpy here. We come up with a new enthalpy. So that's a new enthalpy that we input here. And we also need another intensive property, which is the 600 psi that we input here. And the rest of the table populates. Take notice what happened to the temperature. In the ideal adiabatic isentropic compressor, we went up to a temperature of 485.26 degrees Fahrenheit. But in a real world compressor, we go up to a higher temperature. And why is that? Because the inefficiency of the compressor results in additional heat energy that goes into the fluid. And that's why this is at a higher temperature. For the aftercooler, we have a really easy computation. We know that the inlet conditions are 600 psi absolute and the temperature that we just computed in the real compressor. And we know that the outlet temperature is going to be 100 degrees Fahrenheit. We're neglecting pressure drops, so we know that the outlet pressure is going to be 600 psi absolute. So with that data, we can compute the amount of energy or heat that is rejected to the atmosphere. So using these values, we can see that the temperature at the inlet to the aftercooler is 595.38 degrees Fahrenheit. The pressure at the inlet is 600 psi. Once we put those two intensive properties into the software, the rest of the row populates. And we can see an enthalpy here of 263.28 BTU per pound mass. That means for every pound mass of nitrogen that goes through there, the enthalpy is 263.28 BTUs per pound mass. Let's take a look at the other condition, which is at the outlet of the air cooler. We have 100 degrees Fahrenheit and 600 psi. Once you put in those two intensive properties, the rest of the row populates, and we see a new enthalpy as shown here. And that change in enthalpy is going to be the amount of heat that is rejected to the atmosphere by that aftercooler. And we see it computed here as 127.88 BTUs for every pound mass of nitrogen that goes through that aftercooler. Now let's take a look at the expander. And we put a control volume around the expander. And we see the expander has one input, which is the enthalpy of the fluid going in. And it has two outputs, the work that's leaving the expander and the fluid enthalpy that's leaving the expander. So obviously, the sum of these two has to equal this. Let's take a look at that on the analysis. Looking at the input to the expander, we have 600 psi absolute and 100 degrees Fahrenheit. Once you put those two intensive properties in, the rest of the row populates. And if it's isentropic, adiabatic isentropic, we set the entropy to be equal the entropy in to be equal to the entropy out. So we input this 1.3751 here, and we know the pressure out is 60 degrees, 60 psi absolute. So once we put in these two intensive properties, the rest of the row populates, and we see we have an adiabatic isentropic temperature of minus 173 degrees Fahrenheit. But we also know that this is not an adiabatic isentropic expander, but it's a real world expander. So we have to take the difference of the enthalpy, which is the amount of isentropic work out, and we need to know that it's going to be something less than 100% efficient. In our case, it happens to be 80% efficient. So we take this delta enthalpy, multiply it by 0.8, and come out with a smaller amount of energy. And then we take that amount of energy that comes out, subtract it from the enthalpy in, and we get the actual enthalpy out. So you can see what happens here. If this was an ideal adiabatic isentropic compressor, we would drop this enthalpy all the way down to 69. But it's not ideal isentropic, so we drop it down really to only 82.86. Now let's do the thermodynamic analysis. We know that we need two intensive properties for the inlet of the expander, and we have them here, 100 degrees Fahrenheit and 600 psi absolute. Once we put those in, the rest of the row populates, and we see that we have an entropy of 1.3751. If it's an ideal adiabatic isentropic expander, we know that the entropy in is equal to the entropy out. So we input 1.3751 here on the entropy, and we need one more intensive property, and we have it here, which is 60 psi absolute. Once we input those two properties, we know that the rest of the row will populate. Looking at that, we have a difference in enthalpy. Well, the difference in enthalpy will be the amount of work that comes out. And that's shown here that the difference in enthalpy from 135.4 to 69.733 says that we have a work output from this turbine of 65.667 BTUs per pound mass of nitrogen going through the expander. However, that is for an adiabatic isentropic expander, I should say. And we know that there's no such thing as an adiabatic isentropic expander. So what we need to do is say this is the ideal work that would come out. but we know that we're only going to get 80% of that work. So we multiply this by 0.8 and we come out with a new value of this being the value of the amount of work that's coming out. And the only way we could have this value of work to come out is if this enthalpy that's coming out happens to be 82.866. So we put in here 82.866, and we now put in here our 60 degrees Fahrenheit. And what we find out as the row populates, that we have a new temperature of the outlet of the expander, which is minus 121.51 degrees Fahrenheit, not the minus 173 that we showed earlier as the ideal expander. So the ideal expander would give you the most work out and the lowest temperature, but since there's no such thing as an ideal expander, we're going to be getting a warmer temperature here. Next, let's look at the chiller. Well, what do we have going into the chiller? We show a control volume around the chiller, and what we have going in is the enthalpy of the fluid going in plus the heat going in, and we know that the sum of those two must be the enthalpy coming out. Sounds simple enough. Let's do the analysis. Looking at the chiller, we can see that the delta enthalpy is going to come out to 38.124. That means that 38.124 BTUs per pound mass of nitrogen being sent through the chiller will be removed from the natural gas stream. How did we find that out? We put the inlet conditions to the chiller in here, the pressure and temperature. Those are two intensive properties. And we put the outlet conditions here, which are two intensive properties. And the rest of the rows populate. We look at the delta enthalpy as shown here, and that gives us the 38.12. This slide and the next slide are two of the most important slides in the presentation because it shows how the pressure of the feed gas causes the LNG to produce at a different quality or different composition of methane. Let's take a look at 400 psi as shown here. Our feed gas is cooled down to minus 110 degrees and then flashed from 400 psi down to tank pressure. And induce very little actual LNG and a lot of flash gas. Why little LNG? Because we're very far away from this saturated liquid line and we're real close to the saturated vapor line. And I know that this has very little methane in it because it's boiled off in flash gas. So this would not be a quality LNG, and we'll look at the actual composition of that LNG. Let's bring in the feed gas now instead of at 400 psi absolute, 500, 600, 700. We'll bring it at 700 psi absolute. So we cool down our feed gas to 110 minus 110 degrees. And look how much further along we are when we drop down in a JT valve. We're now 50% or approximately 50% liquid and approximately 50% vapor. And we can go even a step higher, but that doesn't bias too much because it just brings us a little bit more to the left. So it's very critical here going from 400 to 700, less critical going from 700 to 1,000 psi absolute. But let's take a look at this now analytically. When we look at this analytically, we can say that we came in at 110 degrees minus 110 degrees Fahrenheit and 400 psi, and we flashed down to 16.5 psi absolute, which is tank pressure. And we know that This is a enthalpic, meaning constant enthalpy flash process. So we look for our enthalpy, see where that is on here. And the enthalpy should be shown right here. And here's the constant enthalpy. And we see that it's 243.7 going into the JT valve and 243.7 coming out of the JT valve. What is the composition of the LNG that comes out at this 16.5 psi absolute? Take a look here. It's 6%, 6.6% methane, and it's 39, almost 49% ethane, and it's 53, almost 54% propane. So it's certainly not usable LNG. Let's do the same exact process, but now let's have the feed gas up at 600 psi. Well, at 600 psi, we drop down again, and constant enthalpy is shown here. And now we've increased from 6.6% methane to 64% methane. It's still not usable LNG because it has too low of a methane content, too high of an ethane content, and too high of a propane content, but it is certainly significantly higher than we had with the lower feed gas pressure. We have a problem. We've made a chiller, but it doesn't get cold enough. So how can we drive this chiller temperature down colder? Well, one way we can do that is increase the inlet pressure, but that's not very effective because the temperature difference across this expander is a function more of the compression ratio than of the pressure inlet. So the pressure ratio does not get affected very significantly as you raise the inlet pressure, but it does get significantly impacted as you lower the outlet pressure. So if I lower the outlet pressure, I can certainly get more work out and get a colder temperature. That's one method, but one of the problems there is the lower this pressure gets, the larger this compressor has to become because the density of the nitrogen going into it decreases. Another way of making this chiller colder is to put a heat exchanger in here and take some of this chilling and cool down the inlet to the expander. That would make the outlet of the expander even colder, and we can get a certainly colder temperature here. Now we might not make as much LNG, but what good was making the LNG earlier since it's not usable? We want to get this chiller temperature down further. Let's take a look at that. Earlier, we looked at having the inlet to the expander being at 100 degrees Fahrenheit. Now let's put a heat exchanger in here and exchange heat with the chiller so that the inlet temperature to the expander is 0 degrees Fahrenheit instead of 100 degrees Fahrenheit. Let's see how that affects the outlet of the expander temperature, which is the inlet to the chiller temperature. Now we're going to bring the inlet to the expander temperature down to 0 degrees Fahrenheit by exchanging heat from the inlet to the expander to the chiller. If you want to see the actual computations, the mathematics of doing that, go to the course that's given on thermodynamics. It would be the last course, which would be 3B. Part 3B of the thermodynamics course. This is what our new process would look like. We now have an inlet temperature to the expander of 0 degrees Fahrenheit. Let's take a look how it's going to affect the outlet temperature of the expander and the operation of the chiller. For the mathematics of this, you can go to the course on thermodynamics. But just let's take a look at what happens at the outlet of the chiller. We're able to bring the LNG temperature down to, it looks like approximately minus 175. And when we flash down, we're now getting a higher, much higher amount of liquid natural gas, much less vapor is produced, and it's going to be a higher quality of LNG. Let's analytically look at what the quality of that LNG is. So with us bringing the temperature of the inlet to the expander down to 0 degrees Fahrenheit, the outlet nitrogen of the expander comes down to minus 185 degrees Fahrenheit. And the LNG, or the feed gas that's being chilled to LNG, comes down to minus 175 degrees Fahrenheit. Now keep in mind, this is 100% liquid, even though it's at minus 175, and that's because it's at an elevated pressure. It's at 400 psi absolute. So here we are with our inlet condition of 400 psi absolute and minus 175 degrees Fahrenheit. Our feed gas is 94% methane, 5% ethane, 1% propane. Our enthalpy is 63.825, and we're going across the JT valve, so it's an isenthalpic process, meaning constant enthalpy process. And you see the enthalpy in is equal to the enthalpy out. And we're going down to tank pressure, which is 16.5 psi absolute. And now what's happened to our methane concentration? A methane concentration becomes 91.06% methane, and that was from a feed gas of 94% methane. So a significant amount of our methane has flashed off, but it still gives us now a usable LNG. But it's quite high BTU content. It has a 1089 BTU content, which means its Wabi index will also be high. So we want to look at now how can we make it even colder so that this methane concentration gets even higher than the 91%. Let's transfer more heat from the inlet to the expander to the chiller. Now we're getting a chiller inlet temperature of minus 117 degrees Fahrenheit. And I actually selected that intentionally, a strange odd number, minus 117, in order to get a temperature here that is actually saturated LNG, 100% LNG coming out here. So let's take a look at that numerically. With the inlet of the expander being at minus 117 degrees Fahrenheit, we see that the feed gas can be brought down colder, colder, colder. And right now it looks like, reading this chart, it's about minus 256 degrees Fahrenheit. When we flash down in a JT valve, you see we're right at the saturated liquid line. So we're producing LNG 100% saturated liquid. This composition should be the same as the feed gas, 94% methane, 5% ethane, 1% propane, and no flash gas if we bring it down to this very cold temperature before going through the JT valve. So this is very desirable because we get a LNG that has a lower BTU value and a lower Wabi index. So that is allowed to remain interchangeable even as it was. So far, we've looked at just producing a chiller and making it cold enough to make LNG. But it was definitely not an efficient process that we were using. So let's look at how to improve the efficiency of this process. The above exercise just got us to the point where we said, hey, there's proof of concept that this process does work. But to improve efficiency, we have to do many other things like multi-stage expansion and multi-stage compression. This is a much more advanced process. You see there are one, two, three, four compression stages, and there are two expansion stages. So let's follow this process. This is your main nitrogen compressor, and it compresses up to 300 psi. Then it has an intercooler, gets rid of heat. This is a much more efficient way to compress. Then it goes into a second stage compression and it compresses again, this time from 100 degrees Fahrenheit up to 900 psi absolute. And we'll use the mathematics to calculate the temperature of this. And if you want to follow the mathematics, go to course number 6, which is section 3B of the thermodynamics, and it has all the mathematics done in that course. And you reject heat again to the atmosphere. Now, the atmosphere is 90 degrees Fahrenheit outside, so we're looking at getting this nitrogen down to approximately 100 degrees Fahrenheit. Goes into this heat exchanger, is cooled down, brought down to minus 50 degrees Fahrenheit. We're still at 900 psi, and it is expanded down to 200 psi. Remember, I said the expansion ratio is what's important, not the actual numbers that you're dealing with. So we're going from 900 to 200, and that expansion ratio would be a 4.5 expansion ratio. 200 divided into 900 gives you 4.5. And that expansion ratio gives you a very cold temperature here. We're not showing it here, but it's in the computations. And after it extracts heat from the feed gas, it is now warmed up to minus 155, goes into this expander, gets very cold. Again, we're looking at a compression, or I should say an expansion ratio. We're going from this pressure here, which is 200 psi, divided by 30 psi, gives us our expansion ratio. And go from minus 155 to a very much colder temperature, which has been computed in the course 6, and probably show it late. Well, I do show it later on in this presentation. Now it's very cold. It extracts heat from the feed gas, making this LNG subcools, goes into the JT valve, and that LNG goes into your LNG tank, and it may or may not have flash, depending upon what temperature is shown here upstream of the JT valve. Coming out of the expander, goes through this heat exchanger, extracts heat from the feed gas, goes through this heat exchanger, extracts heat from the feed gas, goes through this heat exchanger, extracts heat from the feed gas, and now we have our nitrogen that's going to be recycled back into the process. It's at 30 psi, gets compressed, rejects heat, goes into this compressor, rejects heat again, then goes into our main compressor. We have two main compressors, A and B, in this particular process. And these two main compressors are really probably on the same shaft, but they're two stages. This is stage 1 and this is stage 2 with intercooling in between. Let's take a look at what else we're doing here. We have bog, which is boil-off gas, which is very cold. So we're using that bog. We're extracting the cooling from that bog or absorbing heat from the feed gas using that bog. In this exchanger, which is your C exchanger, your B exchanger, and your A exchanger. And I've just named them A, B, and C for simplicity. And then your bog is now warm bog, and that goes out, gets odorized, and gets sent out to the customer. This is the same drawing, but now we've done some computations of the amount of work that's being transferred from this expander to the compressor, from this expander to the compressor, and we've also put in some temperatures that were computed, and this one here is minus 176, just approximately minus 176. And this one here is down to minus 262 degrees Fahrenheit, which what we saw before with that minus 262, it's cold enough to get a feed gas that would turn into 100% liquid before and after the JT valve. Now, I made this drawing a little bit simplified in that I did not put the bog stream in it, and that I did just for ease of computations. But the computations are not done in this presentation. They're actually done in the course number 6. But this one is more conceptual to show you the outcome. In this slide, I show you the total work and heat balance, and the total amount of work in and the total amount of heat in will equal the total amount of heat out. And that's nothing more than the first law of thermodynamics with a control volume around the entire plant. And you see I added a lot more detail in here as to the computations that were performed. And now we have to some degree optimized this process. Now we could have optimized it even further, but in engineering, there's always a balance between how much efficiency you want and how much you want to pay for that efficiency in the form of capex. So we've gone significantly more complex and more expensive in our capex to make this more efficient. And you can make it more efficient yet, but it's a cost capex. It's a capex versus efficiency engineering decision that needs to be made on that. And if you really want to get efficient, you go to an MR system, which is a much higher capex process. But there again, it depends on what you want. If you're going to be doing peak shaving for a plant that's going to operate for a small period of time during the year, well, then you'd want to use a nitrogen system because your capex is low and your opex is higher. If you're going to do a lot of liquefying, let's say you're an export terminal, then you would want to use something like a C3MR, very high efficiency process that has a very high capex but a lower opex. And the last thing you want to do with all your computations is put a control volume around the entire plant and make sure that everything balances. This way you make sure you don't have any hidden errors in your computational work. And in this case, 180.43 equals 180.43, and those are in BTU per hour, and it checks, so we know that that computation is correct. The process I showed you earlier was a closed expansion process, and this one is an open expansion process. What that means is that high pressure gas comes into your plant and low pressure gas leaves your plant. And that pressure energy is used to drive expanders that produce shaft work, and expanders will drive compressors. And you have a process, an expansion process that's going to produce refrigeration so you can make LNG. So this high pressure gas comes in and gets compressed further and then gets compressed again. Now we could have put an intercooler in here. I chose not to for this design. Then comes out of this compressor, goes into a aftercooler, comes out of this aftercooler and splits into two streams. One stream is going to be your refrigeration stream, and your other stream is going to be your liquefaction stream. This becomes feed gas that gets liquefied. Let's follow the refrigeration process. We come into this heat exchanger and we cool this gas down from 80 degrees down to minus 80 degrees. Go into this expander and we cool it down to some very cold temperature. I haven't computed it here yet, But if you're interested in the computations, it's shown in the thermodynamic course. So you come into this expander, come out very cold, go into this heat exchanger, and you extract heat from your feed gas stream, which is the feed gas which is coming here, which to make LNG. Come out of this heat exchanger, go into another expander. And again, we come in cold, but we come out very cold. Now we're down to 15 psi G. That's about 30 psi absolute. And this gas is very cold. It goes into this process heat exchanger, I should say, and it extracts heat from the feed gas. Now here it splits. It goes into this heat exchanger and extracts heat from the feed gas, but it also goes into this heat exchanger to extract heat from your refrigeration gas. And this is the balance valve that balances how much of this gas is going up into this exchanger to cool down feed gas and how much gas is going into this exchanger to cool down refrigeration gas. And the combined flow of what goes through the liquefaction process exchanger and what goes through the refrigeration process exchanger, this combined flow is what's sent out to your distribution system. And your distribution system has to be capable of taking this large amount of gas pretty much 365 days a year. Because if you want to run this refrigeration process during, let's say, July 4th, when no one is using gas, everyone is out watching the fireworks, well, you've got to take all of this gas, and in this particular case, I'm looking at 2 million standard cubic foot of gas per hour, 2 million standard cubic foot of gas. That's about 50 million standard cubic foot of gas per day, and is being sent out to the distribution system at 15 psi. So you need very large gas mains with a large distribution system to take this gas away. Let us look at the feed gas process. The feed gas started here, got cooled down further. Now this exchanger is an interesting one because we have no part of the expander outlet going through it. What this expander is doing is it's taking the flash gas. Remember, we're going across a JT valve and we are producing flash gas, which is very cold. Flash gas is at in the order of magnitude of minus 200 145 degrees Fahrenheit, depending upon what this temperature, what this pressure temperature equilibrium is. I say it's 15 psi gauge, so I'm guessing at that minus 240, but in the course on thermodynamics, it's actually computed. And that goes through this heat exchanger, gives up its refrigeration by extracting heat from this feed gas, continues on, extracts heat from the feed gas, continues on, extracts heat from the feed gas, and that too is mixed with your tail gas that's going out to the distribution system. So what's happening here with this feed gas? Well, it's 100% liquid at this point. Goes through the JT valve, flashes to liquid and vapor. The liquid is sent to the LNG tank, and the vapor is sent out to the distribution system. This is an open expansion liquefaction process.